So this is section 2.3, day 2. So in day 1 we talked about continuous functions. So remember the general rule of thumb for continuous functions is if you can draw it with your pencil without lifting the pencil, then the function is continuous. And then we also talked about types of discontinuities, and we had 4 of them, and they were jumps, holes, asymptotes, and oscillations. And so now today we're going to talk more about continuous functions and their properties. So continuous functions have properties that are similar just to numbers. If the functions are continuous, then we can add the functions, we can subtract the functions, so we have sums and differences. We have a product, so we can multiply the functions. We have, I'm going to skip down to 5 here, we have quotients, in other words, we can divide the functions as long as the function in the denominator is not 0. And then back up to 4 here, we've got constant multiples, which means we can kind of scale the function up or down. In addition, I know you've talked about composite functions in pre-calculus, and we're going to talk a little bit about composite functions here as well. But basically, if we have f, if f is a continuous function, it's continuous at c, and g is continuous at the y value f of c, then we know that the composite g of f, in other words, if we take f and stick it into g, that would also be continuous at c, and we'll talk more about that a little bit later. So let's talk about this idea of a continuous function, and this is just a page that kind of helps you build the foundation here. So like I said, a function is continuous, so let's take a look at this function here. If we start at some point A and we draw this function and we end up at point B without lifting our pencil. And so if we have that continuity then, if we have that continuous function, then we can pick a value in between, a y value, in between the A and the B values here. So this line represents some random y value. And if we start out with a function here that is below that intermediate value, and the function is continuous, then if we draw that function and go up to the ending value at b, we've got to cross that line at least once. And so that intermediate value, then we have to reach that intermediate value at least once if the function is continuous. And so kind of expanding on that, okay, so we're getting a little mathy here. Really what we're saying is we have these same 2 values, a and b, and we have that same intermediate value, we're going to call it w. And so in this case, this continuous function crosses that intermediate value w 3 times. So it's got to cross at least once, but it could cross several times. And so this really gets at then what the idea of an intermediate value. So if we have this intermediate value here, so it's between, we have w and it's between f of a and f of b. In other words, w is some y value between these 2 y values. And so we call it an intermediate value because it's in between. And so with our continuous function here, if this value is an intermediate value, then the locations, the x locations where we cross that intermediate value have to be inside the domain of a to b. So they've got to be somewhere in between a and b. And so that's what we call the intermediate value theorem. And we'll get to that in just a second. These last 2 screens were from www.mathisfun.com, and this website's really useful for explaining calculus concepts for the new calculus learner. So if you want to have some nice explanations of what's happening in calculus, that's a good site to hang on to. So we're going to look at this statement a little bit more now and introduce it as the intermediate value theorem. So the intermediate value theorem goes like this. We have f of x and it's continuous. That's represented by the black curve. And it's continuous over the domain from a to b. Remember, these are domain notations here. Then we can pick a y value, f of c. That's our w. We can pick some intermediate value. We're going to call it f of c. And that intermediate value is between these 2 y values. So it's this intermediate value is between these 2 y values. Then there must be at least one value c, so one x value within the domain. So one x value within the domain that corresponds to that intermediate value. And like the previous screen showed us, there could be possibly more than one, but there's at least one. And so that's our intermediate value theorem. And so before we talk a little bit more about that, I want to talk a little bit about discontinuities and whether or not it's removable. And looking for discontinuities is kind of like Where's Waldo, but it's easier. So for instance, if I asked you to find the point of discontinuity with this piecewise function, and it's typically piecewise functions are the type of questions that these are asked with. Finding the point of discontinuity is not hard at all. We just have to look right here. So the point of discontinuity is that location, that x value, where we transition from one function to the next, and we transition at -1 here. Okay, so let's take a look at whether or not this discontinuity is, first of all, whether we have a discontinuity, and if we do, whether it's removable. So the first thing we could do is look at the graph. So for instance, if we graphed 5 plus x for all values less than -1, then we would get something that looks like this. We have an open dot at -1, 4, because when we put -1 here, we get a value of 4, but we don't include that value because we don't have the equal to sign here. So we have an open dot here, and then as we go to -2, that we'd be at 3, and as we go out to -3, we'd be at 2, and so on and so forth. So as we look at this one then and graph this one, when we're exactly equal to -1, we have a y value of 3. So there's that value exactly at -1. And then this last one here, when we're greater than -1, we have this line, slope of -1/2. If we distribute the -1/2, we can see we have an intercept of 3/2. So we can start here and go down 1, right 2, down 1, right 2 to get our points. And so when we look at this, we can see that we have 2 open circles and 1 value that's not on either one of those functions. So we know that we have a jump discontinuity, which is not removable. So looking at the actual function values at this location requires us to plug -1 in for each one of these. And so on the red graph, we're up here at 4, if we could include it. On the middle graph, we're at the value 3, and on the bottom graph, we're at the value 2. So showing that these are all different values is another way to show a jump discontinuity. So this is not removable, because it contains a jump here, and so we'd have to leave that discontinuity as is. We can't remove it. So let's work on how we make a piecewise function continuous. In other words, if we go back to that last graph, how can we make it so that all 3 of these values come together at a single location, so we don't have to lift our pencil in order to draw it? So let's talk about this one. Notice we have a C and a D here. We don't have these defined values. But we know that the point of possible discontinuity is here, and we want to remove it. So we want to make sure we plug any holes, so to speak. So we know this is a parabola, and we know this is a line. And so we want to find the value that makes the constants C and D such that at x equals 2, we have the same y values here. So this is equal to this and is equal to this. So, so we're going to start with the function that has no constants to find a value for f of x. So that means we're going to start up here. So we're going to use that parabola, x squared minus 4x. We're going to plug in 2. So we have 2 squared minus 4 times 2, and that equals -4. So we know we want all of these y values to be -4. So that being the case, then that means C has to be -4. And that means D plus X has to be -4. And we know that we're evaluating this at 2, so when we plug in 2 and solve this, D has to be -6. So our piecewise function then is going to look like x squared minus 4x for values less than -2. That's this parabola. It's going to have a value of -4 at x equals 2, so that's going to be my filled in dot. And then it's going to have the line minus 6 plus x for values that are greater than 2. And that's going to cause the parabola and the point and the line all to come together in a single location, which means when I draw this with my pencil, I can draw the parabola, color in the dot, and go right to the line without lifting my pencil. So just for a summary here, what criteria has been met for the function to be continuous at a point? We know with the left limit, the right limit, and the function value have to be the same. So in other words, we got to match all of those values up at a single y value. And what's our working definition of drawing continuous functions? That's a continuous, the function is continuous if you can draw it without lifting your pencil. Okay, so a continuous, I should have had the word function in there. A continuous function is drawn without lifting your pencil. So at this point, if you're in class, we have a limit and continuity activity to participate in. So it asks, we have this thing that's up on the board. It's called the world's longest piecewise function, and you are given an x value, and we have to find the right hand limit, the function value, and whether or not the limit exists, and whether or not the function is continuous. And so if you're in class, that's what the activity that's going on at the end of class. And then after you're done with the activity, like for instance for me, I would say that we're approaching 0 from the left hand. I'm on function j, and that equals 6. And if I'm approaching the 0 from the right, in other words, the bigger values, I'm on function k, and that also equals 6. And so since these are approaching the same y value, the limit does exist, and the limit is 6. Just because the limit exists doesn't mean the function has to have the value of 6, though. In this case, the function does have a value of 6. So since the limit and the function value are all the same, we have a continuous function. So in other words, as I go through at the point x equals 0, I don't have to lift my pencil at all, and I can keep drawing right through that point. So after the activity is done, you should be ready to then work on the homework for section 2, 3, day 2.